Yes, I'm Kendra Johnson, and I'm representing the Global Earthquake Model Foundation, in particular the hazard team. We're based out of Pavia, Italy, and I'm happy to be presenting on behalf of our team today. So the purpose of the presentation that I'll give today is to introduce probabilistic seismic hazard analysis in hopes that members from all different angles who are interested in using PSHA or who are interested in contributing to PSHA understand how we go from data to results and how those results end up impacting applications. And so this is a very conceptual introduction and high-level introduction. I won't have time today to go into a lot of the details that I would like to. It's too much for 1 hour, but I hope that this gives you an idea of the main things we're thinking about when we're using PSHA and developing models. So I'll start out by introducing the GEM Foundation a little bit more, as well as our Global Seismic Hazard Mosaic and Map and the OpenQuake engine. And the reason for introducing these two main activities that GEM carries out is they're very useful for leaning on examples as I go through this presentation. And then the bulk of the presentation will be about PSHA itself. So I'll start by introducing the hazard integral, so the main construct that's used to help us develop PSHA models and to compute hazard curves that are ultimately giving us values that can be used in engineering, design, or risk applications. The second part is the presentation of the main components of a PSHA model. And finally, I'll go over the common outputs in their applications using, again, the OpenQuake engine as a exemplary point. So the GEM Foundation is a nonprofit public-private partnership, and we have the vision to create a world that is more resilient to earthquakes. And I've listed here some of our core principles: openness, collaboration, credibility, and public good. And we accomplish these, or we aim to accomplish these, by developing and providing an open source software for hazard and risk calculations, and as well as maintaining global coverage of hazard and risk models that are formatted for this engine, facilitating use by our participating organizations and the wider public. And so one of our main tasks is keeping up to date this global seismic hazard mosaic and map. And the global map, the global mosaic is composed of a number of different probabilistic seismic hazard models that are covering different regions, sometimes large regions, for example, the whole of South America, sometimes smaller regions, for example, just the country of Papua New Guinea. And we've taken these models, or they've been contributed by different organizations, different projects, or sometimes developed by the GEM Secretariat, and we've put them into the OpenQuake engine format. And we use these to help us get a general sense of the global hazard and how it varies from place to place. And today I'm going to use these models to as sources of examples for each of the concepts and methodologies that I'm demonstrating. So I've mentioned a couple times now the OpenQuake engine. And what is the OpenQuake engine? So this is the software developed by the GEM Foundation. It's an open source tool for probabilistic seismic hazard and risk assessment. And today we're just focusing on seismic hazard, but I want to make known that there's a risk component as well. So the engine is coded in Python, and it's accessible on GitHub at the link listed here. And initially, I stated GEM is the developer of this software, but actually it's more of a community effort. So GEM leads the development, but as you can see on our GitHub page, we have a number of different contributors who are either coding up different functions that are useful as new literature becomes available, providing tests, these sorts of things. And the engine runs on all of the most common operating systems, including those listed here. And it's tested against both unit tests, so every individual function is tested, as well as compared to other PSHA codes and benchmarks. And so we consider it to be a fairly robust tool for these calculations. So focusing a little bit more on the hazard components of the engine, what can you do with this engine? And so I've listed the main calculators from the hazard side. We have scenario-based analyses in which we're looking at just a single earthquake event and trying to understand the impact in terms of shaking that we would see given that earthquake. So the main output of this is a ground motion field. The second and third components I've listed here are more probabilistic approaches to seismic hazard analysis. So the first listed in blue is classical PSHA, and this is the one that I'll be describing the most today. And the second is event-based PSHA. So just to give you a little introduction before we actually dive into what constitutes a PSHA model, the outputs that are coming from this are hazard curves, hazard maps, uniform hazard spectra, and these are different ways of demonstrating how the seismic hazard is changing over different time scales and how it's changing spatially, as well as for different types of assets. So complementary to the OpenQuake engine, GEM also produces a number of different toolkits that both come on the front end, helping to develop a seismic hazard model, and on the back end, in which we're testing the models. And so I'll use a couple of these in my examples that I provide as well. Okay, so without any more delay, I'll get into what PSHA is. So the goal of PSHA is to reduce the subjective judgment in seismic hazard calculations, but while still recognizing the aleatory or random nature of earthquake processes, as well as the impact of our limited knowledge and data about earthquake processes on hazard results. So ultimately, we are trying to understand the regularity of damaging ground motions that occur due to earthquakes. And to this end, PSHA calculates the likelihood that a site will experience a given level of shaking that's higher than some value in a time period T. And the way we express these results varies a little bit depending on the application. But these are three of the most common ways of expressing the results. We have the annual rate or frequency of exceedance. And so this is the number of times per year that a ground motion is exceeded at the given site. The inverse of this is the return period. So the time interval between occurrences of this threshold. And then finally, the probability of exceedance. And so this is the likelihood that that ground motion or larger will occur during a given time. And these values listed at the bottom of the screen are simply highlighting a few of the different probabilities of exceedance and listed in their different expressions that are commonly seen in applications of PSHA. So I've listed 10% in 50 years and 2% in 50 years. And these are some numbers that come up a lot for building codes, for specific design projects. And so we'll see these a little bit more as we go on through the presentation. So the approach we use to computing hazard results is to use the hazard integral. And this is an integral, a construct that allows us to consider all the possible seismic sources that could cause damaging ground motions at a site of interest. And so we'll break this down a little bit into its individual components. So the output of the hazard integral, the value that we compute, is a rate for a single site at which a ground motion, here it's called IM, intensity measure, for some specific intensity measure type, exceeds a threshold of X. And so the way of computing this is to consider every single source, all sources I equals 1 through n, and how the occurrence rates of those sources are magnitude dependent, and all of the different earthquakes that they could produce. And so what does this mean? It means that each source can produce ruptures of a range of magnitudes m, and that these sources will have, or these ruptures will have different distances between the site and the source, the rupture itself. So these distances are called r, and we're considering every single one inside of the integral. Then we say for each given rupture, what is the probability that the ground motion level will be exceeded at the site? So wrapping that all together, we're considering every rupture that could be produced by every source and trying to understand the likelihood of a ground motion level at the site given each of those ruptures. So the output of the hazard integral is a single hazard curve, and that hazard curve corresponds to one scalar metric, which indicates the level of ground shaking. And so we call these intensity measure types or scalar metrics. And there are a range of these that we'll go into a little bit more once we talk about the ground motion component of PSHA. And each hazard curve also corresponds only to a single location and assumes a single site condition. For example, a single rock type or soil column. And on the right here, we have an example of a hazard curve. And we'll spend a lot of time understanding these with the hazard results. But to give a little bit of an introduction, on the x-axis, we're showing the intensity measure level. So the shaking is getting stronger as we go to the right. And on the y-axis, we're indicating the annual probability of exceedance. So as we go up the y-axis, these shaking levels are becoming more and more common. So I've indicated on this hazard curve three horizontal lines that correspond to the probability of exceedance that might be considered for different types of structures. And so this helps you to start to see why hazard curves are useful. So how do we actually create a model that we can solve with the hazard integral? So this consists of three different components. The seismic source characterization. And so this is one or more seismic source models, and taken together, the source model represents all of the seismicity that could impact the region or site of interest. Second is the ground motion characterization. And so these use a set of equations or tables that estimate what the level of shaking will be at the given site when a rupture with certain parameters occurs, some rupture that's admitted by the seismic source characterization. And then finally, we use logic trees, which are structures that allow us to incorporate epistemic uncertainties into PSHA calculations. And we'll go into more detail when we talk about logic trees about what an epistemic uncertainty is. So starting out with the seismic source characterization, one seismic source model includes all sources impacting hazard at a site. So what is a seismic source? It's a simplified description of something that's actually occurring in nature. So in nature, we may think of earthquakes as these ruptures occurring on faults that we can make some simplified characteristics of. So each of these seismic sources needs to be represented by parameters that are essential to solving the hazard integral. So we'll go through each of the main steps for that today, but I've bulked them into three main steps. The first is to identify the actual earthquake sources. The second is to characterize the sources according to the properties required by the hazard integral. And then the third step is to account for the epistemic uncertainties in steps 1 and 2. And in principle, steps 1 and 2 comprise a single seismic source model, and this is actually enough for solving the hazard integral. However, it's good practice to also account for the epistemic uncertainties. So step 1, identifying the earthquake sources. What are the main ways of doing this? So I've started out by indicating a map of different tectonic region types. And this is a good way to get a high-level overview of where, what kind of geologic features are producing earthquakes. And so in particular, I'll draw your attention to plate boundaries. And so these are areas where we know that there's a lot of motion going on at the Earth's surface and at depth. And so we expect earthquakes or some sort of seismic moment release to be occurring at these structures. So I've listed the 3 main types of plate boundaries here. We have convergent boundaries, so subduction zones, continental collisions. Then we have continental or oceanic transforms, where earthquakes are, or sorry, where plates are moving laterally relative to each other. And then we have mid-ocean ridges, which may produce earthquakes, but are to a lesser degree impactful to a lot of onshore sites, given their location in the ocean. Despite that, other sources are not deforming as much. Interplate sources also do occur, and so we also need to be attentive to these. So here I've listed interplate sources within subducting slabs, or also active or stable shallow crest. So these are away from the plate boundaries, deep non-subduction sources, and volcanoes. So the second data type that we can use is seismicity. So we're actually looking at where earthquakes have occurred in the past and using that as a guide to understand where they might occur in the future. And so here I've shown the ASSHEE GM extended catalog for Turkey and the surrounding areas. And each of these dots is a single earthquake. And so we can see that to the west, there's a lot more seismicity occurring than to the south, for example. And so we can kind of use this as a guide to understand where we can expect future earthquakes to occur. And lastly, I've listed active faults. And these are structures that have been mapped by geologists or otherwise, and that they have deemed active and therefore potentially capable of hosting future earthquakes. And faults in the simplest form can just be a surface trace that's indicating where the fault is, but they can be more useful in seismic hazard analysis when we also know the rate at which the fault is moving and a little bit more about its geometry in the subsurface and the sense in which it's moving. So once we've identified where seismic sources are, we need to assign each some parameters that indicate the main characteristics of their rupture generation. And so I've listed these here as the main earthquake source parameters: position and geometry, the magnitude frequency distribution, a corresponding tectonic region, magnitude scaling relationship, and rupturing mechanism. And we'll go through each of these in the following slides. So the first step in defining a seismic source is to choose which source typology will be used to represent the source itself. So how are we going to take the real source of seismicity and represent it by something with the simple parameters needed for the hazard integral? And I've divided these into 2 main categories here: faults and diffuse or distributed seismicity. And this is sometimes also called background seismicity. So faults are 3D surfaces delineating where ruptures occur. So the panel on the left is showing an example of a fault source. in which there's an actual surface that's specified. But on the other hand, when we don't have enough confidence to model a fault source, we can use distributed seismicity sources to represent seismicity that we know occurs, but we can't easily attribute to a specific structure. And so now we'll go into a little more detail about when each of these is appropriate to use and how to characterize it. So fault sources are ideal since they actually correspond to some physical structure in the Earth's crust. And because of this, the modeled earthquake rupture geometries and positions are more accurate than in distributed sources. And so these are commonly used to represent subduction interfaces as well as crustal faults. So what's required in order to use a fault source is that we have known or well approximated 3D fault coordinates. And secondly, that we have some sort of seismicity rate or data that can be used to make estimates of how productive the source will be. So most commonly, we would look for a slip rate. The limitations are that infrequent and lower magnitude earthquakes often don't provide sufficient information for us to constrain the structures that these are occurring on. So for example, crustal earthquake surface ruptures are not common for earthquakes that are smaller than magnitude 6 or even 6.5. And likewise, geological processes are sometimes occurring at faster rates than these infrequent earthquake events, even the ones larger than magnitude 6. And so the evidence of these might be erased. So as an example, you may have an earthquake that causes a surface rupture, but then a flood that follows and wipes out the evidence of that former rupture. So drawing on an example from the global hazard mosaic, we'll take a look at the Popeye, New Guinea subduction interface. And so this model includes two subduction interfaces corresponding to New Britain and Solomon subduction zones. And in the top left image here, the colored contours are drawing from slab 2.0 model, which is indicating the geometry of the subduction interface. And the colors are indicating depth. So the red is the shallow part of the subduction zone. And as it transitions to orange and then yellow and green, it's getting deeper and eventually leaving the interface itself and starting to correspond to the top of the slab. And to the right are the earthquake epicenters colored by their depth. And so these are showing the same properties that at the shallow extents of the slab. We're having shallow earthquakes, and as you move to the north for the New Britain and to the northeast for the Solomon subduction zones, the hypocenters are starting to increase with depth. So the modelers here took these two data sets, and they were able to use them to develop complex fault sources. So these are fault sources with very finely discretized surface geometries. And so that's what's shown in the bottom right here is the geometry and position of these complex fault sources. A second example is coming from the model covering the Philippines. And to the left here is a plot of the fault database maintained by FIVOLCS, the National Volcanology and Seismology Agency in the Philippines. And the line types used in this plot are indicating the sense of motion, the fault typology. And so we have a combination of some dextral faults, some subduction thrusts, and so on. And each of these faults was used to construct a simple fault within the fault model for the Philippines PSHA. And so on the right here, each of the red lines is indicating just the surface trace of one of those faults. So moving on to distributed seismicity, this is useful when the seismicity can more easily be constrained to a zone or a 3D space than it is to a specific structure, as in the past examples. And there are two main types of these. there are area sources, which are polygons within which the seismicity is assumed to occur at the same rate. So there's no spatial variability within the area source. On the other hand, there's smoothed seismicity, in which similar workflow is used as to area sources, but in the final steps, the occurrence rates are varied across the polygon based on some sort of data, such as the locations of past earthquakes. And so areas where we expect more earthquakes to be occurring will see higher rates modeled within the source typology. And these are commonly used for shallow crustal sources, subduction intraslab sources, and any other place where small earthquakes are frequent or strain is observed. But we don't have enough information to use a fault source. So a couple of examples of these. This is drawing from the South Africa model, which uses area sources to model the crustal seismicity. So on the left, you can see the plate boundaries drawn with the colored lines, and then the seismicity that's occurring in these areas. And it's not a lot of seismicity, so it becomes quite difficult for them to take these earthquakes and create specific structures for the earthquakes to occur on. So instead, they've drawn polygons that are bounding certain areas and given a constant rate in those areas. You can see on the right, the more frequent earthquakes are colored in a brighter red, and those are corresponding to the same areas as where there's dense seismicity. On the other hand, we can use distributed seismicity, and so this is drawing from an example in South America in the region of Colombia. And so in this area, we're actually using two source typologies to model the crustal seismicity. And so the red lines here indicating shallow crustal faults modeled as fault sources, whereas the points are indicating gridded point sources that have smoothed rates. And if we overlay the seismicity here, again, you can see that the hot colors, the yellows, oranges, and reds are corresponding to higher rates of crustal seismicity, as opposed to these areas where that are colored in white or in dark blue. So once we've defined the source typology and the geometry of the source, we can turn to the magnitude frequency distribution. And so this is what's used to indicate the rate at which earthquakes of each magnitude might occur. And I've shown three of the major types of magnitude frequency distributions at the bottom of this plot. And on the left, we have the Gutenberg Richter. And so this is a negative exponential. And using this model, we assume that the rate of earthquakes decreases with magnitude. And it's following this negative exponential shape. The second type is the characteristic model, which is assuming that there's one or a small range of magnitudes that are going to do most of the moment release for a certain source. And so in this case, we've indicated this with a Gaussian, but it could be a boxcar, even just a delta function. And then the third type is a hybrid type, such as the one proposed by Youngs and Coppersmith, that combines both of these. So it releases most of the moment in these larger characteristic magnitudes, but still allows some smaller earthquakes to occur as well. So looking a little bit closer at the Gutenberg-Richter relationship, again, this is a source. This is for a source that produces earthquakes of smaller magnitudes more frequently than the larger magnitudes. And the functional form of this is shown on the top right here, indicating that the number of earthquakes can be defined by the rate of all earthquakes, and coefficient that's indicating the relative distribution among magnitudes. So the ratio of the high to low magnitudes. It's also defined by a minimum and a maximum magnitude, so it's bounded between these two values. So how do we actually solve for a magnitude frequency distribution? One of the most common ways, in particular when the Gutenberg Richter is used, is to take a look at catalog observations. And so in this instance, the magnitude frequency distribution, the MFD, is fit to the incremental observations. So the term incremental here means that we're looking only at the earthquakes occurring within a bin. So each of these blue dots in the plot corresponds to only the specific bin that it's plotted in. So earthquakes magnitude 5 to 5.1, 5.1 to 5.2, and so on. This is in opposition to a cumulative rate, which is considering not only the bin that the data point corresponds to, but all larger magnitudes as well. So this is a distinction that you'll often see when looking at these magnitude frequency distributions. So the example shown here is using a maximum likelihood estimator that incorporates time variation and completeness. So what is completeness? This is taking into consideration that we know that seismic networks have a time variable completeness threshold in the magnitude of earthquakes that they're detecting. So a network that's evolved more recently is detecting a lot smaller earthquakes and over perhaps a larger geographic range than the original networks that were deployed. And these detecting more earthquakes than, for example, what we can recover only from word of mouth and historic earthquakes or journal documentations of these. So this, in this instance, this is using a method that's finding the A and B values that are most likely to produce a function similar to what we observe in the incremental observations. So an example is shown here using GEMS Hazard Modeler's Toolkit. The top image is pointing to the magnitude completeness that we have just described. And it's taking a source in central Italy, and it's showing that the perimeter of the source is used to cut the catalog so that it can use only the earthquakes that were produced from that source in order to produce an MFD. And expanding on this, we have an example from central Italy. So this is taken from the SHARE project, the former model about to be updated that covers most of Europe, and showing the magnitude frequency distributions for three different area sources here. And so the red source is showing the highest rates of seismicity compared to the blue source, which is only producing a few small earthquakes. So a second approach to constraining magnitude frequency distributions is to use seismic moment budgeting and balancing. And so in this instance, we are first finding the total moment that we think a source can produce, and then we're distributing it across a range of magnitudes that we think are practical and given a functional form. And so the equation for seismic moment is printed here on the left, and it's taking into account the area of the source. Should I carry on? Okay. The equation here is showing the seismic moment as a function of the area, the slip rate, the coupling across the fault, and the rigidity, and then showing the integral that's used to sum up the contribution of each magnitude. And so the example on the right here is showing a characteristic Gaussian MFD, for example, for a fault source. An example here is drawn from the Cascadia subduction interface as it's represented in Canada's 5th generation seismic hazard model. And here they used a Gaussian, a little bit of a distorted Gaussian function. And so the blue line is showing the incremental magnitude frequency distribution, and the orange is showing the cumulative MFD. So in both of these instances, there's a very important parameter that must be constrained, and this is the maximum magnitude. And in the case of a Gutenberg Richter magnitude, or one that's constrained by seismicity, it may just be that this is permitting larger and larger earthquakes, but at lower rates. But in the case of the moment balancing, this could actually move the entire MFD up and down, which can have a pretty big impact on the rates of all earthquake magnitudes. So there are a number of different approximation methods available for constraining maximum magnitude, and most of them are using some combination of observations, statistics, observations of seismicity, statistics, the local geological features, in particular, for example, fault area, and using these to try to make an estimate of the magnitude. So 3 of the methods are shown here. One coming just from observed seismicity, the one shown on the top left, is simply to add a delta value to the maximum observed in the catalog. The second shown on the top right here is the cumulative moment method. And this is an approach that sums the total moment of all the released, of all the earthquakes that have been observed, and says, what would the magnitude be if all of those earthquakes moments had been released in just a single event? And the third method listed here is to use a magnitude scaling relationship. And this is an approach in which empirical relationships that have been trained by past earthquakes and observations has been used to link magnitude to some dimension of an earthquake. And so, for example, the area or the length of the fault that can rupture. And so the maximum magnitude can be computed as what would occur in a full fault rupture. So there are just a few other source properties that have to be assigned once we've got the geometry and in the magnitude frequency distribution. And so first, to complete the rupture geometries, we need a mechanism, a rupturing mechanism. So the strike, dip, and rake. A magnitude scaling relationship to determine the size of the ruptures. So this is the same as was used in the maximum magnitude instance. A rupture aspect ratio that controls whether the ruptures are more square or more rectangle. Some depth limits that are constraining the upper and lower limits of the ruptures, and a hypocentral depth, this in particular for distributed seismicity. And finally, each needs to be assigned a corresponding tectonic region. And this comes into play more once we look at the ground motion characterization. So just to finally return to this difference between an area source and a smooth seismicity source, once we've defined all the properties that correspond to the area source, we can decide to either keep the rates constant across the entire area source. So that's what's shown in the right here, or we can use smooth gridded seismicity. And one of the approaches for doing this is shown here, in which each earthquake that has occurred is identified and used to distribute rates with some 2D kernel across a grid that represents the area source. And so then the impact of each of the earthquakes is combined. And in the end, the areas that have been more productive in the past or closer to sites that are more productive will have a little bit higher rates than are away from the observed seismicity. So finally, we have all the main characteristics of the seismic sources. And we recall that source itself is not enough to solve the hazard integral. We actually need to compute ruptures. And so the example I'm showing here is demonstrating how we generate ruptures from a fault with simple geometry in the case of the OpenQuake engine. And I will clarify that different calculation engines make different assumptions, but a lot of them can be somewhat similar to this one. So Here what I'm showing is how we use the magnitude frequency distribution, starting with the minimum magnitude, and we combine the rupture aspect ratio and the magnitude scaling relationship to make a single rupture. So that's what's shown here in gray. But the source can produce a number of different ruptures using these same constraints. And so we start to float them across the fault surface until we fully covered the surface. And then the rate that is emitted by the magnitude frequency distribution is divided among all of those different ruptures. We move on and do this for every single magnitude, filling the fault with these ruptures as well. And so these are the ruptures that actually go into the hazard integral calculation. So we've completed the seismic source characterization. We now know how to build one seismic source model. And so now let's take a look at the ground motion characterization. So a ground motion characterization is one or more ground motion models that's used to estimate the ground shaking that will occur when the ruptures of the seismic source characterization occur. So the way that this manifests in the hazard integral is inside the integral, there's the probability of an intensity metric being exceeded given a rupture. And in the output, it's the rate of these ground motion thresholds occurring. And so again, we're looking at that rate just for a single site and a single site condition, as well as a single intensity measure type. So what am I referring to with these ground motion parameters and intensity measuring types? So I've listed here in this table a few of the common IMTs that are used in seismic hazard analysis. So the top two are peak ground velocity and peak ground acceleration. You'll notice the word peak, and this is used because in seismic hazard, we're looking only at the highest value that occurred rather than something like the duration or the full waveform. We also do this for spectral accelerations that are occurring at different vibrational periods T. And these we like to look at because rather than what's occurring on the ground, as in PGA and PGV, we want to see what occurs for structures of different heights and different typologies that have different natural vibrational periods. And then finally, the macroseismic intensity, which is a bit different because it's a unitless value with a discrete scale indicating the severity of earthquake effects. So what impacts ground motion levels? I'm showing here some of the most important variables. So namely the magnitude of the earthquake. As magnitude increases, so do ground motion levels. And then the site to source distance. So as the distance increases, the ground motion levels are more likely to decrease in most cases. The site conditions and the tectonic region type. And this tectonic region type factor is the reason that we have to specify this for each of the seismic sources in the source model. So the method we use to predict the ground motions for a given rupture are with these empirical models called ground motion prediction equations, which compute a scalar parameter value that indicates the ground shaking intensity. And so the simplified functional form is shown on the right here, where y is the ground motion value. And it's a function of the set of explanatory variables, the magnitude, the distance, as well as a set of model coefficients, and then a random variable delta. And this random variable comes in because, as you would expect in nature, we're not seeing a precise, tightly constrained range of values for each set of explanatory variables. And so the plot on the left here is indicating this, showing that the way that the recorded ground motions shown in blue are distributing around the mean prediction, and then that standard deviation term is shown as a PDF. So here's an example of a GMPE, which in addition to these controlling parameters that we've mentioned so far has evolved to be quite a bit more complex, including things like a style of faulting term, whether or not the earthquake is thought to be an aftershock, whether the site is on the hanging wall, and so on. So how do we choose GMPEs? There are hundreds of different GMPEs developed for various tectonic region types, geographic regions, intensity measure types, and so on. And the OpenQuake engine documents these all in the GMPE library. And so I'm just pointing you here to that website where you can see for each GMPE, what is the IMT and what are the different values that are needed in order to use the GMPE. So this gets you a start, but in order to narrow down those hundreds of GMPEs, you can start by using exclusion criteria. So these eliminate certain GMPEs based on their tectonic region type, what parameters they can compute, which geographic region they're intended for, and which magnitude and distance ranges they're intended for. And so hopefully this helps to pare down the data set into something that's more applicable to the model in question. Beyond this, we can use both qualitative and quantitative assessments. So starting with comparative scaling, in which we take a look at how the GMPs are behaving at different extremes that are included within the model, and how this compares to the other GMPEs' performance in these instances. In the optimal case, we use GMPE data comparisons, in which we can compare ground motion recordings for the area to the predicted values from the GMPEs, and find values that have small find ground motion models that have small residuals and are ultimately performing well in that area. So this concludes the ground motion characterization component. And so now we'll take a look at the logic tree structures, recalling that these are the structures used to incorporate epistemic uncertainties into PSHA. So why are we concerned about uncertainty? There are many instances that we can look at from the past where there have been 2 or more reasonable independent studies of PSHA that produce drastically different results. So here I'm showing an example where the EPRI and LLNL have computed very different hazard for a specific site. And so we look for some sort of a method to allow us to use the different assumptions that both studies made and incorporate them into our calculations. And so the first type of uncertainty we need to account for is aleatory uncertainty. And this is the type that's intrinsically related to the earthquake process and actually cannot be reduced. So we need to incorporate it on the inside of the hazard integral. So an example of this might be a hypercentral depth distribution for distributed seismicity, in which we know earthquakes are occurring at multiple different depths. So rather than assigning a single value, we assign multiple values and give different levels of probability to each depth value. Then on the other hand, we have epistemic uncertainties, which are resulting from our limited knowledge about a process. And in this case, over time, we expect the uncertainty to be reducible. And so in PSHA, we account for these logic trees by weighting different alternative hypotheses. For example, entire seismic source models, individual source parameters such as Mmax or an A and B value for an MFD, or ground motion models. And each logic tree end branch becomes one realization or one evaluation of the hazard integral. So the schematic here is just showing how this is termed in the OpenQuake engine. And it's set up in a hierarchical way where we call these branching levels. And each branching level is corresponding to a specific epistemic uncertainty. Here we're showing dip as well as seismogenic depth limits. So an example taken from South Africa, we'll revisit this again, is that each area source is using multiple branching levels. So the initial source has 2 different estimates of Mmax, as well as 3 different A and B value combinations. And so in the end, there are a total of 6 branches for this individual source. Getting into a site-specific analysis, this is likely to grow to account for more and more different uncertainties. And then likewise, we can apply this in ground motion prediction equations. So this example is taken from the interface sources used for the Philippines, in which none of the 4 GMPEs shown here could be deemed more accurate than the others, and therefore all were taken together. So now that we have the components understood, we can go into the hazard calculation results. And I'll show these 4 types on the right here, and I'll describe them as we describe them for the OpenQuake engine. So first, we're now revisiting that hazard curve that we previewed at the beginning of the presentation. And recall that the hazard curve is showing the probabilities or rates of exceedance for a set of ground motion parameter levels for a single site. And these are the primary result of a PSHA calculation. Each hazard curve is one solution to that hazard integral. So the plot is showing examples that highlight some of the concepts that are important to understanding PSHA results. So in addition to the mean hazard curve, the one shown in black, I'm also showing in gray the hazard curve computed for each individual realization. So this allows us to compute not only a mean hazard, but some statistics indicating, for example, different quantiles that are admitted by the hazard model. I'm also, again, indicating some of the common probabilities of exceedance shown here. The second typology is a hazard map, and this is showing the spatial distribution of ground motion parameter levels that have a uniform probability or rate of exceedance. So the example shown here is indicating how for each site on the map, we have to go to the hazard curve and get the value where the hazard curve intersects that annual probability of exceedance. So here we're showing two different probabilities of exceedance, 10% and 2% in 50 years. And seeing that at 2% in 50 years, the less common probability of exceedance, ground motions are getting higher, and some of the structures that aren't visible in the other hazard map are starting to pop out. The third type of result is the uniform hazard spectrum. And this is showing ground motion parameter levels for many vibrational periods at one site and for a uniform rate of exceedance. So this is useful when we want to understand how the hazard compares for different structures or different infrastructure that could be built at the same site. And so the example here is showing how the peak ground acceleration at the site compares to that for two different vibrational periods, and usually peaking around 0.2 seconds. And the last example here is the hazard disaggregation. And so this is no longer a derivative of the hazard curve, but something that helps us to understand the hazard curve. So disaggregation is revealing which combinations of explanatory variables, for example, magnitude and distance, are contributing most to the ground motion parameter level at one site for a specific rate of exceedance. So when we look at the hazard curve, we can see that there are parts where there are frequent weak intensity measure levels compared to spots with infrequent strong intensity measure levels. And we may have different sources that are controlling these values. And so we find it helpful to understand what magnitudes and distances and what tectonic regions and positions are producing the earthquakes that are contributing most at those probabilities of exceedance. And this may be useful, for example, for choosing a uniform hazard spectrum to use in design for a specific project or building. The uniform hazard spectra coming from a subduction interface earthquake may vary quite a bit from a crustal one. Okay, so to summarize what we've covered so far, classical PSHA is an evaluation of the hazard integral, and we use a PSHA model in order to represent the components of the hazard integral in a way that reflects the seismicity occurring around the region of interest, and also as a way of computing ground motions that we expect to occur when those earthquakes occur. Finally, we account for the uncertainty in those using logic trees. And we use the outputs of PSHA to reveal the rate at which shaking levels are exceeded at a site, how this varies spatially, how this varies for a range of vibrational periods, and which sources contribute most to the hazard. So I'll just close by, again, pointing you to the GEM Foundation's tools and packages that are useful if you want to explore more how to build a PSHA model and to get into some of the more complex methodologies than what I've been able to present today. And by providing you with some additional references that can help you learn more about PSHA. Lastly, the bottom on the list is the PSHA training manual that GEM developed as a part of the recent TREC project, which is a example-based manual that exploits our toolkits. And I'll close there and just say thank you again for your attention today. And if there's time for some questions, I can take some questions. Thank you.
Thank you, ma'am. Thank you so much for such informative and wonderful session. Now I request Dr. Devajit Hazarika sir to say something on concluding remarks.
Okay.
Thank you so much. Yes, thank you, Professor Johnson. It was an excellent talk on the topic Introduction to Probabilistic Seismic Hazard Analysis. I think before conclusion, I think there will be some questions, and I will request the participants to put their questions on the chat box, and then we'll go for the conclusion session.
Okay.
Ma'am,
yes.
ma'am, I have a one query.
Yes.
Actually, we are taking linear source. Also, we can take aerial source, right? Which one give the most realistic result in terms of PSHA? And is there any criteria that where we can use linear and where we can use aerial? Because there are many papers are there, many research works are there. Sometimes they are taking aerial also, sometimes they are taking linear source. But because the source, as much as the source is changing, the PSHA value also changing, and everything is depend after 250 to 470. So we don't know which one is the more realistic result, is linear source or this aerial source.
Yeah. Okay. So linear source, also called fault source. I'm sorry I didn't clarify that earlier. Sometimes different vocabularies are also used for fault sources. Again, this is going to depend a lot on how confident you are in the positions of the earthquakes. So if you do have information about the faults that are hazardous to the study site, you optimally do want to use a fault source because it's more likely to indicate the precise rupture locations for the earthquakes that you expect to occur. If you don't have this information, then you're forced to use an area source. There are also instances in which it would be defensible to use completely different source typologies in two different branches of the logic tree. So if you're somewhat confident about your linear sources, but not confident enough, then sometimes models will use the linear sources. So on one branch they're indicating if we're correct about these really precise rupture positions, but then weighting this against another branch in which they relax the positions a little bit more using the area sources. I hope that answers your question.
Just a technical question, may I ask?
Yes.
This is about this uniform hazard spectra. You said that they are for a different nature of periods of structures, but usually they include also damping, normally to 5%. Is it, you are talking about something different or it's the same? You just didn't mention it.
So it's a little bit different, but the concepts are the same. Yeah, so when you would use the uniform hazard spectrum coming out of a PSHA approach, you may apply some damping to it before you actually use it for a design purpose. That is correct. But in terms of the way that the uniform hazard spectra is showing variability in the expected ground motions for a whole range of spectral ordinates, there you're correct that they're the same. Yes.
And another question for the maximum evaluation. This is very interesting for me. I mean, we have a rupture length, and I would like to use the Wilson-Coppersmith relationships to assess the maximum from this. These relationships have their own standard deviation, so it can be treated as aleatory. From the other hand, we may, for example, assume a situation that half of the rupture will be ruptured, so it becomes an epistemic. So what to do?
Yeah, so it's true that you, in some instances, are forced to apply a single maximum magnitude because of the way that the MFD is constructed. So, for example, if you're using a Gutenberg Richter MFD, you're forced to choose just a single M max. So if you want to include that standard deviation, then you must treat it as an epistemic uncertainty. But on the other hand, if you're looking at, for example, a characteristic MFD, oftentimes the reason that you'll see a Gaussian rather than just a delta function is because you're using the standard deviation from those scaling relationships in order to distribute the moment. And so in that instance, once you take the incremental MFD and plot it as a cumulative, you see how the standard deviation is coming into play.
Thank you. And the last question, have you ever checked your probabilistic calculations within these GEM procedures with the deterministic approach? Because you know that, for example, International Atomic Energy Agency, they suggest to control the probabilistic hazard assessment with deterministic approach.
Sure. Yeah, it depends a lot on the application that you're using. But for example, the PSHA approach can be used with disaggregation to decide which scenarios to use in the deterministic case, for example. Yeah, I pointed to the scenario calculator at the very beginning of the presentation, and this is a way of using the deterministic approach as well. So it of course depends on what your application is also, because in some instances, for example, insurance and risk calculations, the deterministic approach doesn't work as well, because then it prohibits considering the consequences of smaller earthquakes, as opposed to design, where depending on the design, you know, a nuclear power plant versus a typical dwelling, the design you want to consider is different. The threshold you want to consider and the likelihood. Yeah.
Thank you very much. Thanks.
Ma'am, another question. Is there any way to incorporate the conditional probability thing? Suppose in a fault we are taking the taking the data from last 50 or so 70 years for the V value and this lambda. But if a big earthquake happen in somewhere, some place, then this thing is actually drastically changed, because the strain accumulation and stress accumulation in this fault will be changed. Is there any, we are calculating the PSHA value for 475 years or 50 years like that, but within this 10 years, the whole scenario could be changed. So is there any way to incorporate the conditional probability thing in the PSHA?
Yeah, I think you're referring to, for example, time-dependent hazard. So what I presented today is time-independent, which assumes that we don't know which.
Some disturbances, no problem. You can carry on.
Okay, no problem. I'll continue. So the approach I presented today is the time-independent, which means that we don't know where in the process we are. We don't know how recently a large event occurred. But there's also the time dependent approach, in which when a large earthquake happens, the rates change a little bit. You know, we know how much moment was released. We know that that means the likelihood in the next 50 years of the largest earthquake occurring again becomes smaller. And so these approaches are possible. I personally am not as knowledgeable about time-dependent PSHA, but one of our models in the Mosaic, the model for Japan, does include a time-dependent component, and so it's possible to incorporate these in the OpenQuake engine as well.
Ma'am, there is a question. In GEM earthquake software, hazard parameters like maximum and minimum are calculated by which methods?
Okay, so so I should clarify a little bit the difference between the OpenQuake engine software and the toolkits used for building the models. So the OpenQuake engine will take input files in which the user has already specified in the model what the minimum and maximum magnitudes will be. On the other hand, the hazard modelers toolkit, the model building toolkit, for example, they provide a number of different methods for computing the MMax, so including the ones that I listed today, in which you can use a scaling relationship or the cumulative moment, and so on. In terms of the minimum magnitude, the user has to be thinking about this in a few ways. So it depends on whether you're using moment budgeting and balancing, or if you're using a Gutenberg Richter, in which you're assuming the A value corresponds to magnitude 0 earthquakes. And so in the latter case, where the relationship is stable, irregardless of what the minimum and maximum magnitudes are defined as, the function of M-min becomes sensitivity in terms of, will they produce ground motions that are large enough that they will change the hazard observed at the site for the probability of interest. And so, so this is evaluated using sensitivity tests where the user will actually do some comparisons where they change M-min. On the other hand, in the case when the moment budgeting and balancing is being used, the M-min needs to be assigned still by the modeler, but considering different factors like how small of earthquakes we think are expected to be accounted for in the data type that we're using. So if you're using, for example, a slip rate across the fault, do you think that that is accounting for every earthquake, or only the earthquakes that have reached the surface and were observed in, for example, a paleoseismic trench that may have been used to back out the slip rate? It becomes a little more complex when the moment budgeting and balancing is being used.
Thank you so much, ma'am, for clearing our queries.
No problem.
Yes.
Now I request Dr. Devaji Hazarika, sir.
Yes, I have a query.
Yes, sir.
Dr. Kendra. Can you hear me? Can you hear me, Dr. Kendra?
Yes, I can hear you.
It was a very comprehensive, very wonderful lecture today, and I think it has been very much beneficial to our students, particularly civil engineering students. As you know, I'm a researcher in seismic hazard analysis. I try to understand the earthquake processes and tectonic part of it. I have a query that you have said the maximum magnitude earthquake is observed maximum plus del. Now, what is that del? Do you suppose specifically I'm asking for Nepal segment of Himalaya, where we have magnitude 8.2 maximum in 1934, and most recently in 2015, 9.8. Now, what for this particular segment of the Himalaya for seismic analysis, what magnitude, maximum magnitude you will use? What will be the criteria
Okay, so when you're looking at a segment like this where you can kind of take the length of the segment and potentially compute the area and then use a magnitude scaling relationship. This will give you a second estimate that you can at least compare with the bounds of the magnitude you compute using scaling relationships plus the standard deviation to the largest one that's observed. But what you're likely to end up doing is considering multiple different values of delta that are becoming less and less likely in your logic tree. And so in one branch, you may say, okay, it could be 0.3 larger than what we observed. 0.3 is a pretty commonly used value. And then it's a little less likely, but possible that it could be 0.5 units of magnitude larger. In the Himalaya, it's also quite difficult because there aren't very many good analogs in other parts of the world that we can look at to say what's the likely largest thing. You know, it's similar to a subduction, but it's not a subduction of oceanic crust under continental crust. It's different in that way, and so the uncertainties remain pretty large for a lot of reasons, and it's an unfortunate thing that has to be grappled with.
Yes, I think another uncertainty is that the earthquake's nature of faulting. In your equation, I might have missed whether you consider the faulting process, whether it is by thrust faulting or strike slip faulting, whether a different bearing on your seismic hazard analysis. For example, the north of MCT, say 2015 7.8 earthquake, it's a typical thrust faulting earthquake in Nepal. But if the 1934 earthquake, which is at the south, to the south of MBT, it is by strike slip or some strike slip component. Now, have to consider this process of earthquake, means faulting nature for your seismic hazard analysis. Another query, please.
Yeah, so this component shows up in the ground motion models. And you know from seismology that a strike slip fault will create different lobes of high energy than compared to a normal or a reverse fault. And so this is also, of course, observed in the ground motions that are used to constrain a ground motion prediction equation. So when these ground motion prediction equations are developed, the records that are used to constrain the model, to calibrate the model, are divided into their predominant categories. So there will be a strike slip faulting set, a reverse faulting set, a normal faulting set, and these will manifest as a term that's used to either scale or add or subtract from the value that's computed from the other controlling parameters.
Thank you so much.
Yeah.
Continuation of this, ma'am, sir. Continuation of this question, sir, ma'am. Can you tell that means we can actually apply the logic tree method into that? If the area is subjected to thrust faulting strike slip, both can occur. So depending upon the logic tree, can we assign some logic point 0.1 logic suppose weightage to the strike slip or thrust faulting? So which one will be more chances of getting that area? So also we can incorporate logic tree method in that area also, right?
Yes, and depending on the source.
If you use more than one or two GMP, ground motion prediction equation, then also.
Yeah, so most of the ground motion prediction equations use just a single term. So it's just, yes, it's strike slip. Yes, it's normal. It doesn't use the rake angle exactly. But within the source model, so you have two options. If you are modeling distributed seismicity, you can actually specify nodal planes as aleatory uncertainties in the same way that you did so for the hypocentral depth distribution. So for example, we may take a whole catalog of focal mechanisms and see yes, in this area, we have both strike slip faulting, that's left lateral, as well as thrust faulting. And so then we might say, okay, in the focal mechanisms, we see 70% are reverse mechanisms with this orientation, and likewise for the strike slip. And so a PMF is created for those as well. In the case of fault sources, at least in the OpenQuake engine, then it's necessary to use different branches where the rake angle is actually being changed. But you can indeed account for these. One clarification I'd like to make that I didn't have time to go into in the presentation is that it's important to remember that for every uncertainty that you add, the logic tree is getting larger and larger and larger, and the calculation time is increasing by more and more. And so it's important to do sensitivity analyses on these parameters to see how much they're actually impacting the computed hazard before incorporating them into the full model and finding that the computation time is huge or impossible, but the change would not be so much in the actual hazard. This is one reason that for a national or regional model, there may be a little less exploration into the epistemic uncertainties than when only a single site is being evaluated.
Yes,
Any more questions?
sorry, one more question.
Yes.
You noted that with this machine, we are getting less subjective solutions. Okay, I understand, and I admit that with these formalized methods and with this OpenQuake belongs to these methods, we have repeatable result. This is true. Mm-hmm. But how we can say that we have a less subjectivity, because the source model we have to elaborate ourselves, and this is no one of logic tree can help, because then I am giving the weights, which is also subjective. Choosing of GMPs, there are so many places where it's hidden explicit or implicitly. This subjectivity is built in. So repeatability, yes, it's definitely solved the problem. But how you feel that subjectivity also reduced?
Yeah, it's true that there are still a ton of modeling decisions that have to be made, and you just, in the end, the decision has to be made based on what the modeler thinks is most likely. So the subjective decisions are certainly not eliminated. However, it's possible to consider at least more than one likely result. And so when so the decision maker doesn't have to choose between two hypotheses that they can't exclude by some other criteria. They can't say, it won't be this, so I should include it. And then because of this, while there's only one mean hazard that's computed, the range of results is also possible to compute. And so from this respect, even though, yes, there were still subjective decisions made, we understand better the range of ground motions that can exist. In the largest level projects, the shack projects, for example, if you're looking at a nuclear power plant, there are workflows that are used by the committees responsible for developing these logic trees that help a little bit with the decision making. But you're absolutely right that it's impossible to completely eliminate the subjective decisions.
Thank you.
Ma'am, another question is there. Mr. Kosen is asking, do you have any training video in YouTube?
Yeah, I see these questions popping up about the training. Yeah, I think I'll go ahead and copy into the chat the link for the Trek training. So Trek was a project that we worked on recently to. Oh, whoops, I have to send it to the whole meeting. Everyone, there we go. So I just sent a link to this. So Trek was a project we recently worked on to increase the capacity for performing seismic hazard and risk calculations on a global scale. And we were in particular focused on Latin America, but I think this is useful elsewhere. So the link I just sent is not a video, but around this website, you can find some other training videos. And we have not yet recorded one on PSHA, but that should be coming in the next couple of months, as well as one on PSRA, so for risk analysis as well. But the ones you can see now are introducing the OpenQuake engine as well as scenario analyses. So it's a start, and keep an eye on the page, and soon we should have the hazard ones as well. The probabilistic ones as well, I mean.
Any other questions? So if no, then we can conclude. At the very outset, thank you very much, Professor Johnson, for your very clear and very comprehensive lecture on the very interesting topic, the introduction to probabilistic seismic hazard analysis. And you have started with the conceptual introduction to the probability seismic hazard analysis particularly to the students and researchers, those who are listening to you. And most importantly, many of us may be knowing about the OpenQuake engine, but you have elaborated the utility of the OpenQuake engine. And also mainly you have focused on the main components of the PSA. It was really interesting, and everybody has taken a lot of interest. I would like to thank all the participants, Professor Ruben, Professor J.R. Kyle, sir, and all the participants, those who have interacted with you. It was really an interesting time. I, on behalf of organizing committee, would like to thank you again. Thank you so much.
Yeah, thank you so much for having me.
Thank you so much.
So much. Thank you for accepting humble request.
Thanks to all. Bye.
To spare your
Thank
time.
you.
Thank you so much.
Thank you so much, sir, for chairing up the session. Now we want to convey our small token of love from the students of Techno College of Engineering, Agartala, to our guest, Professor Canra Johnson.
Excellent.
Very nice.
Actually, we have to, we wish to see the artists, those who are doing this.
Actually,
Yes.
sir, in the valedictory session, we will do that. Please,
Yeah.
sir, you
Excellent.
please present, sir, at that in the valedictory session. We will do that, sir.
Great, great. That's great.
Really wonderful.
Interesting. Really interesting.
Very
Very
nice.
Actually, ma'am, actually, we don't have any good picture of you. So that's why we have taken this IBS WGST. So whatever we have, just don't have any other picture. That's why there's the problem.
But still excellent.
It's very nice, yes. Very excellent. Thank you.
Thank you. Thank you so much. Thank you.
Bye.
Now I would like to request J.R. Kyal, sir, to grant us the permission for concluding today's session.
Yes, please.
Thank you, sir. We will start our fifth technical session tomorrow at 11 a.m. So we will join with the same link by 10:45 a.m. for fifth technical session by Professor J.R. Kyal, sir, from NIT Agartala. Stay tuned and stay safe. Thank you all. Good night.
Thanks a
Thank
lot.
you.
Bye.
Good night. Thank you. Good night.
Good night.
Tomorrow I have, Babu. Tomorrow I have got the